All right, I've got another more theoretical example here, rather than pure computations like you have in most of your questions. Let this set, V1, V2, V3, be an orthogonal basis for a subspace of R3 that's named W here. And then let this lowercase w be a vector in that subspace W. What we want to do here is use the orthogonality of that basis, V1, V2, V3, to express W as a linear combination of those basis vectors. Okay, so the mission here is to express W in the form some scalar, we'll call it C1 times vector 1, plus some scalar, I'm going to call it C2 times vector 2, and then some scalar C3 times vector 3. Okay. So then in other words, the mission here, we in this scenario, we have a specific vector W, and we have a specific basis, V1, V2, V3. So all of those vectors are known. What we need to do then is to solve for the weights of each vector in this linear combination. We want to solve for C1, C2, and C3. We need to come up with formulas for those guys. And we're supposed to somehow use the orthogonality of the basis to do that. So orthogonality, that refers to inner product or dot product being 0 when vectors are orthogonal. So maybe that leads you to think, well, okay, then I probably want to take some kind of inner product if I'm going to use orthogonality of the basis. So suppose, I'm looking for another color to use. Suppose we take the inner product of both sides of this equation with V1. And I'm choosing V1 arbitrarily, I'm just picking the first one. So I want to take the inner product then of this side with V1. All right. One of the properties of inner product says that we can distribute. So this is equal to C1 V1 dot V1. And also we can pull out these scalar multiples. So this is C1 V1 dot V1 plus C2 V2 dot V1 plus C3 V3 dot V1. And here's where the orthogonality of the basis comes in handy. So because this is an orthogonal basis, each of these vectors is orthogonal to all the other vectors in the set. So V1 and V2 are orthogonal vectors. So this inner product is equal to 0. V1 and V3 are also orthogonal vectors. So this inner product right here is equal to 0. And so we end up with just, this is W dot V1 on this side. So we end up with W dot V1 is equal to C1 times V1 dot V1. So this inner product is not 0, unless V1 is the 0 vector, but then this wouldn't be a basis if V1 was a 0 vector. So now remember the mission was to solve for C1, C2, C3. If we have known vectors, W, V1, V2, and V3. So we could now divide both sides by V1 dot V1. And we have solved for C1. So now we have a formula, C1 is equal to W dot V1 over V1 dot V1. Oh, V1 dot V1. I was already thinking about C2 when I wrote that. So I was thinking, here. So now we could quickly solve for the weight of vector 1 just by taking a couple of inner products and dividing. If we did this same thing, I don't want to rewrite all of it because it's going to be very, very similar. We do the same thing, but we take the inner product of both sides with V2. Then again, we would distribute. So these, okay, this part I might have to rewrite. So this will be V2 here, and then this will be C1, or sorry, C2 V2 dot V2, and then plus C3 V3 dot V2. And so this time, V1 and V2, those are orthogonal. So this inner product will be 0. V2 dot V2, that's not 0, because V2 is going to be a non-zero vector, because it's a basis vector. V2 dot V3, that would have to be 0, because those vectors are orthogonal. And so now you could solve, this is 0, this is 0. We could solve for C2. So if this is C2, this is V2 dot V2, and this is V2, this is V2 here. Then if you divide by V2 dot V2, here, you're going to solve for C2. So C1 is W dot V1 over V1 dot V1. C2 is going to be W dot V2. W dot V2 over V2 dot V2. V2 dot V2. And similarly, if you do the same thing, inner product with V3, then you're going to find that C3 is equal to W dot V3 over V3 dot V3. So now, instead of row reducing, if you remember, you had to solve problems like this on your first exam, and you would set up an augmented matrix where your columns are V1, V2, V3, augmented with W as the constant column, and then row reduce. Instead of doing that row reduction, now you can just take a series of inner products, which is usually a pretty quick computation, quick and easy, and you'll find your weight C1, C2, C3. So we get a much more efficient way of expressing a vector as a linear combination of the basis vectors when we have an orthogonal basis. So this starts to get to why we want to invest so much time in learning how to build an orthogonal basis for a certain subspace, because it does make it easier to come up with coordinates in terms of our basis for any vector in the set.